till now we have discussed basic terminologies of vector calculus like curl, divergence and gradient, surface integration, volume integration, line integration. So these all are basic terminologies which you must know before entering in main core topics of vector calculus. So we have discussed all these things. So now we are in a stage to understand the basic theorems and laws which are mentioned and used in vector calculus. So at this level you only need to know about Gauss's law and Stokes' law. Gauss's theorem, Stokes' theorem, they are extensively used in electromagnetism even at higher secondary level. So you must be aware with these Gauss's law, Stokes' law, and from Stokes' law we derive Ampere's law, which is also used sometime in various competitive exams. Ampere's law and Gauss's law are asked. So here we will discuss the core topics of vector calculus, which are Gauss's law and Ampere's law. So first of all, Gauss's theorem. Gauss's theorem is called Gauss divergence theorem. Gauss divergence theorem. What is the statement of Gauss's theorem in mathematical form? So there is a closed surface. First of all, there has to be a closed surface. A closed surface can be any closed boundary like sphere, closed cylinder, any closed three-dimensional boundary. So that is a closed surface which creates a volume, any type of shape which you can imagine, and the corresponding closed boundary will exist for that shape. It can be a spherical shape, cylindrical shape, tetrahedral shape, or any other shape. There are many types of possibilities. So for simplicity, there is a closed hemisphere and there is a field F, vector field. We have discussed what is vector field. So there is a field existing in this space which is surrounded by this closed surface. So for example, this is a spherical surface. So spherical surface, there is a vector field. So what Gauss's theorem says that surface integral of this vector field along this closed surface. We have discussed the surface integral f dot dA. We will divide this surface in small area vectors. This is dA, and the direction of area vector is outside, perpendicular to the surface. For a closed surface, always I have already mentioned, for a closed surface the direction of area vector is always perpendicular to the surface and outward from the surface. So this is a closed surface. So outward perpendicular, that will be the direction of area vector. This is area vector. So f dot dA, we will carry out f dot dA throughout this surface, spherical surface, by the integration method. We will get flux. This is nothing but net flux. What is net flux? Net flux is total algebraic sum of flux through the surface. Some flux will enter in the surface and some flux will exit from the surface. For flux, suppose this is the dA. Here F is in this direction and dA is in this direction. dA is in this direction. So both are in opposite direction. So for this surface, for this region F dot A will be negative, and in this area, let this is dA. So here the direction of dA will always be outward from this closed surface. So that is the direction of dA, and the direction of field, this is also along the area vector. So in this region F dot dA will be positive because both vectors are in same direction. So ideally half of the hemisphere will have positive flux because both F and dA are in same direction. Here also this is dA and this is F. This is dA and this is F. So this normal component of dA will have zero flux, and component of dA along this field will contribute to flux. That will be positive because both are in same direction. And similarly in this left half, whatever small dA area element you select, every time this normal to this dA and this F will be in opposite direction. So the vertical component of dA and this will be the component along F. So this component of dA and field both are in opposite direction. Vertical component will contribute zero flux. So in this whole region, half region, F dot dA will be negative, and in this half region F dot dA will be positive. So that is why we calculate net flux. By this method we calculate net flux. Negative plus positive, when we add all flux throughout the surface, we will get net flux. Or indirectly we can say these flux are entering flux and these are the exiting flux. Net flux is exit minus enter. There is a difference between entering and exiting flux. That is the net flux. So this will give you net flux. Net flux of a field is equal to divergence of this field. Net flux created by this field in this spherical surface will be equal to divergence. We have studied what is divergence, del dot F dV. This is the Gauss's theorem. This is also called Gauss divergence theorem. Surface flux for a closed boundary, net flux is equal to divergence of that field throughout the volume created by the closed surface, dV. So we have discussed what is divergence, how to calculate divergence of a field, what is flux, and how to calculate flux of a field. So this is the Gauss's theorem, which is also called Gauss divergence theorem. This is also written as in double integration form. You can write it like this, and it can be written as triple integration form. You will also see this form also for Gauss divergence theorem. Again I will repeat, net flux of a field through a closed surface are equal to net divergence throughout the volume created by the closed surface. Net flux is equal to total divergence of that field in the volume created by the closed surface. That is Gauss divergence theorem. Similarly, another theorem which is very important in vector calculus, that is Stokes' theorem. So we have seen that Gauss theorem is for a closed surface. Here we have assumed spherical surface, whereas Stokes' theorem is for a surface which is not closed surface, that is open surface. It is for an area, only for area which doesn't create a volume. For that we have Stokes' theorem. So what is the statement of Stokes' theorem? That this is the area, arbitrary area A, and this is the field existing field, vector field throughout this area. Throughout this area, a vector field is present in space. So, the statement of Stokes theorem, that is a statement of Gauss's theorem, Gauss divergence theorem, and Stokes theorem is written as curl of F. This is a vector. We have discussed what is curl. This is nothing but a vector. Dot dA. Surface integration or flux created by curl of this field in this area, given area, and this is equal to circulation, which is line integration, circulation of this path which creates the area. This is a line boundary of the surface. This is the boundary of the surface. So along the boundary we have to carry line integration. That is, for complete boundary we have discussed, we call it circulation. For a closed loop, circulation of F dot dl. That is the statement of Stokes theorem. And Stokes theorem, again I will repeat, Stokes theorem, this is a closed path, and this closed path creates an area, and this is the area. This is a surface. Closed path creates a surface A, and this is the existing vector field. Stokes theorem says that curl of vector field dot dA throughout this surface created by closed curve is equal to circulation of this field along the curve, closed curve. That is line integration in a closed curve. This can also be written as, you know what is curl? Curl is nothing but del cross F dot dA is equal to circulation of F along the curve. Stokes theorem can also be written like this. So these are the two important theorems. Sometime you will see this it like this. See this in double integration form also. That doesn't matter. We have already discussed double integration. You can find flux, volume, divergence, everything by single integration. That doesn't matter what type of mathematical tool you use. You use double integration or triple integration or single integration. That doesn't matter. So their form may be different, but the physical significance, physical meaning is same. This is the flux of curl of vector field throughout this area enclosed by this given curve. Then this is the circulation, which is line integration in this closed curve for field, for a given field F dot dl. So these are the two statements which are called Gauss divergence theorem, and this is called Stokes theorem. So we have discussed Gauss's law for universal field, universal vector field. So here we will see how Gauss's law can be applied for electric field. So as we have seen in Gauss's law, for any vector field, Gauss's law is given by, let the field is F. Then Gauss's law is given by F dot dA, that is surface integral along the Gaussian surface, any imaginary surface, is equal to divergence of field F for the volume surrounded by the Gaussian surface. That is Gauss's law. Now we will see how it can be applied for electric field. So let this is the electric field and this is an imaginary Gaussian surface. So it can be written for electric field E dot ds, sorry dA, that is the flux, electric flux through this Gaussian surface. This is a closed Gaussian surface. So there will be many areas dA. We will divide this whole Gaussian surface in small area elements like dA, dA, similarly here dA. So the flux will be, when we will integrate this electric flux throughout the Gaussian surface E dot dA, and this will be divergence of E. For the volume surrounded by the Gaussian surface. So as per the now we will use Maxwell equation here. As per the Maxwell equation, you need not to go in detail of Maxwell equations. We will just use the simple result of Maxwell equation for low frequencies. For low frequencies, this divergence, that is divergence at a point, for the electric field is given by sigma by epsilon 0 for low frequencies, where sigma is charge density, that is Q by V, charge in unit volume, that is the charge density sigma. So we can write this del dot E. Here we can write it, sorry. So this del dot E can be written as sigma by epsilon 0 in this Gauss's divergence theorem. This is Gauss divergence theorem for electric field. So it can be written as integration of sigma by epsilon 0 dV. This can be, so we have written this divergence part with the help of Maxwell equation in this form. Now sigma is, this can be written as 1 by epsilon 0 sigma dV for the volume. Now sigma is the charge density, charge in unit volume. So sigma dV will be, sigma dV can be written as 1 by epsilon 0 dQ. Sigma dV is nothing but charge enclosed in small volume dV, which is dQ. So Gauss's law can be written for the electric field in this form, and this integration of dQ through the volume surrounded by Gaussian surface can be written as, and this can be written as 1 by epsilon 0 Q, total charge, and this is Q net charge inside the volume surrounded by Gaussian surface. So this is the result of both Gauss's expressions. So Gauss's law for the electric field can be written in this form, that is, this is called integral form. E dot dA flux, this is nothing but total flux through the Gaussian surface, is equal to, E dot dA can be written as Q net by epsilon 0. This is called integral form of Gauss's law for electric field. Q net is net charge inside this volume. It may have some positive charge, some negative charges. So we will algebraically add all those positive and negative charge, and we will get Q net by algebraically adding charges inside this Gaussian volume. So this is the one form, this is called integral form of Gauss's law. Similarly, from Gauss divergence theorem, we know that total flux is equal to total divergence in this volume, divergence of electric field throughout the volume. So we can also write Gauss's law in other form, which is in volume integral of divergence of E dV is equal to Q by epsilon 0. So this can Q net, this is Q net, always you remember Q net is net charge surrounded by the volume. So this can again be written like this, integral of divergence dV equal to sigma dV, where sigma is the charge density and dV is the volume, divided by epsilon 0. This is nothing but Q net. We have used Q net early in this derivation as dQ is equal to dQ as sigma dV. So this can be written as, by removing integral sign, we can write it as divergence of electric field at a point is equal to charge density by epsilon 0. This expression can be written in this form, which is nothing but initially which we have used Maxwell's equation. This is the Maxwell equation for low frequency, which we have used to derive Gauss's law for electric field. So this is also another form of Gauss's law, which is called differential form. So this is integral form. This is integral form of Gauss's law, and this is differential form of Gauss's law. Integral form is achieved by equating this total flux with Q net by epsilon 0, and differential form is achieved by divergence, total divergence of volume surrounded by Gaussian surface with Q by epsilon 0, and it is in the form of charge density. So Gauss's form can be written in terms of integral form and in differential form. Generally we will use integral form to find the electric field, as we will discuss in our later chapters, because Gauss divergence theorem is a universal theorem, and this theorem holds true for any field, not only for electric field. So we will just see how Gauss's law can be used for gravitational field, but it is not frequently used because Newton's law of universal law for gravity is enough to find the gravitational field. But how the Gauss's law can be written to find gravitational field, that we will just see here to understand its universal applicability, understand the universal applicability of Gauss's law. So we know Gauss's law, this is a mass m, this is a solid mass m. Let there is a closed surface, this closed volume or closed surface which we were talking in our Gauss's divergence theorem is also called Gaussian surface. Closed surface is also called Gaussian surface. This is an imaginary surface which we create, imaginary surface, to study the field at a particular point. And this is also very important to create suitable Gaussian surface. Suitable means it can be in spherical form, it can be in cylindrical form, it can be in cubical form. So what type of Gaussian surface we should create to find the electric field, to find gravitational field, that is also a skill, a matter of practice. That is also very important. Gaussian surface, the nature of Gaussian surface, this is up to us how which type of surface we create based on the situation. So we will discuss further how the symmetry is used to simplify the problems in Gauss's law. So this is just a Gaussian surface, an imaginary sphere surrounding this mass m. So we know for this spherical surface, you can let there is gravitational field. This mass, that is the center of this mass, and at these all points there will be gravitational field. So let this is a point P. So by symmetry, we use principle of symmetry extensively in Gauss's theorem. As this is a spherical surface, spherical surface, so all points on this surface are symmetric. From the point, they are geometrically symmetric, as well as any physical property like gravitational field will have same magnitude at all points in this spherical surface, because all points are symmetric and they carry same amount of physical property, which is gravitational field G. So for this spherical mass, a volume surrounded by this sphere is a symmetric volume, and all points on this sphere are identical in all respects, in geometry and as well as for the field also. The magnitude of field by symmetry, you know, will be same at all points in this sphere. So by Gauss's theorem, you can write that G is the gravitational field at point P. So vector G cross dot dA, that is net flux through this Gaussian surface, will be equal to divergence of G in this volume. This is the Gauss's law, which we can write for gravitational field. Now, from Newton's law of motion, we know that G at P is equal to G m by r square, where r is the from center distance of point P from center of this mass. This is the Newton's law. This is known as we have used Maxwell's law to simplify in electric field. Similarly, from Newton's law, we know the value of Gp. So we know that at every point in this sphere, the direction of G is radially inward. Direction of G is radially inward, and so the G and the area vector at every point in this sphere will be radially outward. Radially outward. So by symmetry principle, we have assumed the magnitude of G at all points will be same. And by Newton's law, we know the direction of G will be towards center at all points. Similarly, the direction of area vector throughout this sphere, all small area element will have direction radially outward. As the convention says, the dA is always for a closed surface, dA is always perpendicular to the surface outward. Here dA will be perpendicular to the surface outward. Here dA will be perpendicular to the surface outward, and the direction of dA is nothing but direction of normal on this area, and the direction of normal is radially outward. So this is the direction of dA. So we know at every point the gravitational field and dA, this is the direction of G. Here this is the direction of G. Here this is the direction of. So at all points in this sphere, gravitational field and vector dA are in opposite direction. So total surface integration, total flux will be negative. So this we can write as, because G and dA are opposite direction, so we can say G dot dA is equal to G into dA minus G into dA. For any small element, G dot dA will be magnitude of G into magnitude of dA area, and this will be minus, this is not dot actually, this is into, and this will be negative because both vector G and vector A are in opposite direction. So when we will add the dot product for whole surface, so it will be G will be common, minus G, and dA, small elements of all throughout the spherical surface, this will give integration of dA, this will give total surface area. That is nothing but for a sphere, it is 4 pi r square. Sorry, r, capital R. So this G dot dA for a small area is minus G dA. So G is same for all points. So G you can take common, and integration of dA is nothing but total surface area of this sphere, which is 4 pi square. So this, if you will find the surface integration of G dot dA for this spherical volume, you will get G into surface area of sphere, and this will be negative because at every point G and dA area vector are in opposite direction. By Newton's law of motion, put G is equal to Gm by r square. So this can be written as minus Gm by r square. That is the value of G from Newton's law of gravity into 4 pi r square. And this can be written as 4 minus 4 pi Gm. R will cancel, and this is minus 4 pi G. So surface integration, that is flux due to gravity, is minus 4 pi Gm. This is the statement of Gauss's law for gravitational field, and this can be written as minus 4 pi Gm. This is the Gauss's law for gravity. This we have derived with the help of Newton's law of gravity as well as Gauss's law for any vector field. So Gauss's law for gravitational field we have derived as G dot dA, where G is a gravitational field. For a surface, gravitational flux is equal to divergence of gravitational field through the imaginary Gaussian surface. Now, and this is equal to minus 4 pi Gm. This is the Gauss's law for gravitational field. Now, when we compare this form, that is flux, gravitational flux, with this minus 4 pi Gm, analogous with electric field. So this integral, this will give integral form, and when we compare this part, divergence part, with this minus 4 pi Gm, that will give you differential form. So integral form of Gauss's law can be written as total gravitational flux through the imaginary Gaussian surface equal to minus 4 pi Gm. First form of Gauss's law, which is called integral form of Gauss's law for gravitational field. By comparing this part with this, second part you can see divergence part, this part, divergence part, divergence of gravitational field through a Gaussian surface equal to minus 4 pi Gm, and this can be written as minus 4 pi G integral of dm, total mass can be written in terms of dm, integration of dm. When you will compare this with this, what do you get? Divergence at a point is equal to minus 4 pi g dm over dv. This dm over dv is nothing but density at a point, at a particular point. This is minus 4 pi g rho, where rho is nothing but dm by dv, which is density at a point. So divergence at a point by gravitational field is equal to minus 4 pi g into density at that point. So this is the second form of Gauss's law, that is divergence at a point is equal to minus 4 pi g rho. This is the integral form of Gauss's law for gravitational field, and this is in the differential form. This is called differential form of Gauss's law for gravitational field. Now we will slightly move ahead with the differential form of Gauss's law. Differential form of Gauss's law is this: divergence at a point is equal to minus 4 pi g rho. Now we have discussed in divergence topic, when we take gradient that is written as gradient of any scalar field. Gradient of any scalar field is always a conservative quantity. That is a vector quantity. When we take gradient of a vector field, scalar field, it becomes a vector field, and that vector field is always a conservative vector field. Now we will use the reverse concept. Here we know G is the conservative vector field. So G is a conservative vector field. It will have its corresponding scalar field whose gradient will be equal to G. So G can be written as grad U, where U is the potential energy. Here the scalar function corresponding to gravitational field, which is conservative field. Scalar function corresponding to conservative gravitational field is potential field, and this is negative because gravitational field is a collapsing field. Here divergence is always negative, and this is negative. So here we can replace G as gradient of U. U is the potential function. U is nothing but Gm by R. For a mass m at a distance r from the center of mass, U is given by Gm by R. So just replace G with this in this equation by that gradient of U, that is gradient of potential energy function, which is a scalar function. Potential energy function is a scalar function, and gradient of this potential energy function will give you a vector function which is gravitational field. So we can write here as divergence of this G is minus, so we can take minus here. G is equal to minus grad U is equal to minus 4 pi 0. This can be written like this. So minus minus will cancel. So this will be grad square, and this is also called Laplacian operator. Laplacian of U will be 4 pi 0. This is another form which is derived from Gauss's differential form. Differential form of Gauss. This is another form, and this form of gravitational field is called Poisson's law. This is called Poisson's law, which is also used to find gravitational field. So this form is another differential form. This is the Laplacian. This is actually written like this. Del dot del is del square. Sorry, it is del square. When we will carry out the dot product of del with del, it will be del square. So earlier we have discussed what is del square. Del x square plus del y square plus del z square. This is Laplacian operator. So in the form of Laplacian, the Gauss's law can be written in terms of Poisson's law. Now we will apply Gauss's law in our third known very familiar field, vector field, which is called magnetic field. And here in magnetic field, Gauss's law is slightly different with electric field, different with gravitational field. In gravitational field and electric field, you can compare the analogy with Gauss's law in integral form as well as in differential form. But with magnetic field, Gauss's law, form of Gauss's law is entirely different. So we will just discuss it briefly with magnetic field also. So for magnetic field, just imagine a bar magnet. This is north pole and this is south. Magnetic field will be like this. We will start from north pole and end with south pole. End with south. And inside this magnetic field will be from in this opposite to outside field. The unique property of magnetic field is that magnetic field lines are continuous lines, unlike gravitational and electric field. We know in electric field, this is electric field and this is charge plus Q. All electric field line will start from this point. They will have a starting point, that is plus Q charge. Similarly, in gravitational field, this is mass. So gravitational field line will come from infinite and they will end at the center of this mass. They have end point. And in case of electric field, they have a starting point. Similarly, in minus Q charge, they will also have end point electric field lines. This is electric field line, this is gravitational field line. So here they have starting and end point. But in magnetic field lines are continuous. When the lines are continuous, then whatever imaginary Gaussian surface you can imagine, whatever imagined closed Gaussian surface, you will imagine net flux through the Gaussian surface will be zero. For example, if these are continuous lines of any field, if you imagine a closed Gaussian surface in this field, then net flux, when you will calculate the net flux, like this is field, any field, continuous. From here to here, this is continuous. And in this continuous range, you have assumed a Gaussian surface, imaginary closed volume. When you will carry out this integration to find the net flux through this Gaussian surface, then you will divide it with small areas dA. So these are all dA. You will get for this half, you will get flux by F dot dA. Here you see dA and F both are in same line, same direction. So the dot product will be positive. Similarly, for this half, area vector direction will be in this direction. dA. These are all dA. When you will divide this half of this Gaussian surface, small area vectors this direction of area vector, as we have discussed, will be outward from the volume. In here it will be in this direction, that is opposite to the existing field. So here F dot dA, when you will carry out F dot dA in this range, there it will be negative. So when you will add total flux F dot dA, total flux through the Gaussian surface, you will get 0. For any continuous field, you imagine a Gaussian surface, the net flux will be 0. That is the property of magnetic field also. Here any Gaussian surface you imagine, suppose you are imagining a Gaussian surface here, here, or complete Gaussian surface. In every case, in all these cases, magnetic field lines are continuous. For this Gaussian surface, these are the flux line, magnetic flux line, they are entering in this field, and these lines are exiting from this surface. These lines are entering and these lines are exiting. So net flux will always be 0. Similarly, in this Gaussian surface, lines are entering from here and exiting from here. So entering flux will be equal to exiting flux. Similarly, for whole bar magnet, if you will cover bar magnet through a Gaussian surface, then these lines will exit from this surface and this line will enter in this surface. So net flux through this closed volume will be 0. So whatever imaginary volume you can imagine, you can form, you will get, or you will always get net flux 0 in case of magnetic field. So for magnetic field, as the net flux is always 0, unlike gravitational and electric field, we can write for magnetic field net flux B dot dA through imaginary any Gaussian surface is always 0. This is always 0, unlike gravitational and electric field. By Gauss divergence theorem, we know that total flux is also equal to total divergence of magnetic field. This is total flux. By Gauss divergence theorem, we know total flux is equal to total divergence through any closed Gaussian surface. And as the total flux are 0, because magnetic field lines are continuous lines, they never start or end at a point. They are continuous lines inside the magnet and outside the magnet. These lines are continuous. So total flux is 0. Net flux is 0 for any Gaussian surface. As the net flux is 0, and net flux is also equal to divergence through the volume as per the Gauss divergence theorem. So the total divergence will also be equal to 0. So that is Gauss divergence theorem for magnetic field. It is 0, unlike electric and gravitational field. This 0 always, this form of Gaussian law, Gauss's law for magnetic field also gives a very important conclusion. This says that as why it is happening actually, why it is 0, because this is North Pole and this is South Pole. Lines will start from North Pole and end with South Pole. If there is a single North Pole, just imagine there is single North Pole, then magnetic field line will be like this. And for this closed Gaussian surface, net flux will have some finite value. Net flux will have some finite value, just like any positive charge, electric field. This is electric field for positive charge and this is Gaussian surface. In this case, the net flux, which is E dot A, is equal to Q by epsilon 0. Similarly, if there is separate North Pole, then also this net flux, that is B dot A through Gaussian surface, will be will have some finite value, because these magnetic field lines are exiting from this Gaussian surface and there is no entering magnetic field in this Gaussian surface. Hence net flux through this Gaussian surface in case of this magnetic field will be positive or will have some finite value of magnetic flux. So this B dot dA, total magnetic flux through this Gaussian surface, will not be equal to 0 if there is separate north pole. You know that magnetic poles always exist in paired form. There is never, you will never find a single north pole or single south pole. That's why magnetic field is continuous, always from north to south, outward from magnet, and inside the magnet from south to north. So this says that as magnetic flux through any Gaussian surface is 0, hence single monopole, that is monopole, doesn't exist. Single magnetic pole, that is north pole or only south pole, will never exist. That's why magnetic field flux through any surface, Gaussian surface, is always 0. Had there been a single north pole or single south pole, like this, single north pole, then we will always have definite magnetic flux through a imaginary Gaussian surface. But always you will get north and south pole in paired form. That's why magnetic field will always be continuous. Hence, for a continuous field, magnetic flux will always be 0. That means monopoles, magnetic monopoles, doesn't exist in nature. That is another conclusion of Gauss's law for magnetic field. So we have studied Gauss's law, and Gauss's law is universal law for any vector field. We have studied it for magnetic field, for gravitational field, and for electric field. So we will write the Gauss's law for all these three familiar fields at same place, at one place, so that you can compare their analogy. So for electric field, first for electric field, we have discussed Gauss's law in integral form is E dot dA is equal to Q net by epsilon 0. That is Gauss's law for electric field in integral form. Similarly, Gauss's law for gravitational field is G dot dA is equal to minus 4 pi Gm. That is the Gauss's law for gravitational field in integral form. For magnetic field, Gauss's law is B dot dA is equal to 0 for any Gaussian surface. So this is Gauss's law for electric field, gravitational field, and magnetic field in integral form. Now for electric field, Gauss's law in differential form is del dot E is equal to sigma by epsilon, where sigma is charge density, that is sigma is equal to Q by V. Sigma is charge density. So this is the differential form of Gauss's law for electric field. Similarly, differential form of Gauss's law for gravitational field is del dot G is equal to minus 4 pi G rho. Here rho is mass density. Rho is equal to m by V. And Gauss's law for magnetic field in differential form is del dot B is equal to 0. So we have discussed Gauss divergence theorem for any vector field F is given by F dot dA is equal to divergence of F dV. This is Gauss divergence theorem. So when you compare integral part of Gauss divergence theorem with this, you get integral form of Gauss divergence theorem, Gauss theorem for electric field. When you compare integral part for gravitational field, you get integral form of Gauss's law for gravitational field. And when you compare integral part in magnetic field, then you get integral form of Gauss's law for magnetic field. Similarly, when you compare the divergence part of Gauss's law with q net by epsilon 0, you get that differential form of Gauss's law for electric field. When you compare divergence part in electric field, you get differential form of Gauss's law for gravitational field. Similarly, differential form for magnetic field by comparing divergence part. Another last form was Poisson's law, which we have derived from for gravitational field as del square, that is Laplacian of u potential energy function is equal to 4 pi g rho. This is minus. So this is differential form in second derivative form, in Laplacian form, which can be achieved by differential form of Gauss's law for gravitational field, which we have done in our earlier discussion. This form of gravitational field is called Poisson's law. So these are Gauss's law for different fields. Here you can see the analogy in differential form. This is charge density by epsilon 0, and this is rho. This is mass density. In place of charge density, for gravitational field it is mass density, and for magnetic field it is 0, because magnetic lines are always continuous lines. Now we will understand about how Stokes' law is used in the form of Ampere's law. That this is a magnetic field. So we have written Stokes' law, and this is a boundary. This is a boundary path, and the area bounded by this boundary is A. This is a path, and this is a magnetic field is existing in this region. By Stokes' law, we have seen that curl of any field, we are writing Stokes' law for magnetic field. Curl of any field dot dA, that is surface integration of curl of magnetic field in this surface, is equal to circulation of magnetic field dot dA, sorry, dl. That is a line integration. In a closed loop, line integration in a closed loop will give you a circulation. So that is Stokes' law for magnetic field. So we know magnetic field is equal to mu 0 into H, where H is the intensity of magnetic field. Intensity of magnetic field, and mu 0 is the permeability of free space. This equation you all know. Now as per Maxwell's equation, again we will use Maxwell's equation here, the special case of Maxwell equation, as we have used in electric field. By Maxwell equation, curl of H is equal to J, where J is equal to current density I by A. This is Maxwell's equation, a special case of Maxwell equation for low frequency. Curl of magnetic intensity H is equal to current density, where current density is I by A. So you can write it like this: H is V by mu 0, So you can say curl of magnetic field is equal to mu 0 into J. Maxwell equation in terms of magnetic field can be written in this form. So this curl you can write as mu 0 J. Curl, just put mu 0 into J here. dA is equal to circulation of B dot dl. That is the Stokes theorem. When we use Maxwell's theorem by finding curl of magnetic field as mu 0 A for low frequencies. J is the current density. J dot A, J into A is nothing but J dot vector A is nothing but current flowing through small area dA, because J is current flowing through unit area. J dot A is current flowing through small area dA, and integration of this will give you total current through the surface bounded by this region. So this you can write as, this is nothing but mu 0 into total current. This is I, dI. J dot dA is nothing but dI. So you can write it like this. Mu 0 you can take out, it is a constant. dI is equal to circulation of B dot dl. dI, integration of dI through this surface is nothing but mu 0 into total current. Total current through this area is equal to circulation of B dot dl. Line integral of B along this closed loop. This is nothing but Ampere's law. Here also, similar to Gauss's law in electric field, where charge Q is the net charge, that is total charge enclosed inside the volume after adding plus and minus charge. Similarly, this I is total current flowing through this area. It can be, there can be more than one current, I1, I2, I3, and some current may have opposite direction to other current. So you can take any current positive and the reverse current you will take negative. So Ampere's law, it can be written as in circulation of B dot dl is equal to mu 0 I1 plus I2 plus I3 etc. All algebraic sum of all current passing through this area. So this is Ampere's law, which is frequently used to find the magnetic field. Here we create an imaginary curve, just like Gaussian surface, which is imaginary surface. In Ampere's law, we create an imaginary curve of suitable form, circular or rectangular, based on the situation, to simplify the problem so that dot product can be found without actually carrying out integration. We select curve and surface in Gauss's law and in Ampere's law in such a way so that their dot product can easily be found without actually carrying out integration. Dot product, either both vectors should be perpendicular, field and area vector, or both vectors should be in same or opposite direction. Only then you can find dot product easily without carrying integration. So that is the skill we use to create imaginary curve and imaginary Gaussian surface to find dot product and surface product, this surface integration easily without actually carrying out integration. And then we can found magnetic field and electric field.
So this is the Ampere's law. Again we will discuss it shortly. Stokes' law for magnetic field can be written in this form, which we have discussed earlier. Stokes' law for any general field. For magnetic field, the curl of magnetic field dot dA. This will be vector dA. Curl of any magnetic field dot dA is equal to circulation of magnetic field along the closed curve, which creates whole surface. So this is a Stokes law. Now by Maxwell equation, we know magnetic intensity, curl of magnetic intensity is current density. Current density J is I by A. Unit vector through unit area, current flowing through unit area. H is the magnetic intensity, and relation between magnetic field and magnetic intensity is given by B is equal to mu 0 H for free space. Mu 0 is magnetic permeability for free space. So this equation, Maxwell equation, you can write like this: curl of magnetic field is equal to mu 0 J. Now put this curl of magnetic field here is equal to mu 0 J. This is mu 0 J. J is the current density. J dot dA is equal to B dot dL. So this mu 0 J and J dot dA is nothing but dI. That is current flowing through small area dA. So this can be written as mu 0 dI. Mu 0 we have taken out, dI inside integration is equal to circulation of magnetic field around this closed curve. dI, integration of dI is nothing but total current flowing through this area. Mu 0 into I net. Here also we can write as I net. Just like charge Q net, total charge Q1 plus Q2 plus Q3. Here we can write total current enclosed by this curve. Total current mu 0 into total current is equal to circulation, that is B dot dL in this closed curve. So circulation of closed curve is equal to mu 0 I1 I2 I3, I1 plus I2 plus I3. That is the standard form of Ampere's law. So we can write Ampere's law, circulation of B dot dL is equal to mu 0 I1 plus I2 plus all addition of all current flowing through the imaginary curve, closed curve. So in both cases, in Gauss law and in Ampere's law, we use imaginary surface and imaginary curves to find magnetic field, electric field, gravitational field, etc. And again I have told you, as I have told you, you need not to carry the actual integration. We will discuss in example. So we have to find Gaussian surface and Gaussian curve, this curve in Ampere's law skillfully, intelligently, so that the dot product becomes easy and you need not to carry out actual integration. Only then the Gauss law will simplify the problem. Otherwise there is no meaning if you are actually carrying out integration, then there is no meaning in simplifying the problem. It is actually complicating the problem. So Gauss's law, you have to select Gaussian surface so that area vector and field, their dot product throughout the surface can be carried out without integration. That is E dot A. E dot A is simple only when either both vectors are perpendicular, then their dot product will be 0, or both vectors are along the same direction or along the opposite direction, then their dot product will be product of their magnitude only. If they are in same direction, dot product will be positive, and if they are in opposite direction, dot product will be negative. So we select surface and curve such a way the dot product throughout the surface and throughout the curve can be achieved without integration.